Okay, welcome to Friday's live stream. Today we're going to do a grayscale operation. Well, actually, it's more of a luminosity operation. It's not. So there's different ways you can calculate grayscale. The simplest one is you add all three values together and you divide by 3, giving you an average or a grayscale image. I like using the luminosity. So let's see. Let me pull up a luminosity equation. RG. So the So I guess I have to check out different things. So this equation right here is what we're looking for. And I believe this equation converts to that in a way. I'm not sure what the plus 16 is at the end. But this is that equation is provided by Xilinx. Received option 1. I'm slower to calculate. Yeah, so there's a lot of ways you can calculate grayscale. It's not as straightforward as you want. So Xilinx provided this in one of their app notes, and it's my to-go-to determining the luminosity of a pixel, or the grayscale value. So we're going to instantiate a new source here. We're going to create a file. It's going to be VHDL, because I like VHDL. And we're going to call it GreyScale. Why not .vhd, virtual hard drive? Sure, why not? Finish. So we're gonna have clock inputs. We have a valid. We're gonna have RGB. And it's gonna be a bus, and it's gonna be 23 bits wide. And let's add another one. It's gonna be the output, which is gonna be gray V or whatever. Output, it's going to be a sign of 7 bits. Okay, yeah, let's go ahead and do it. So first off, let's get us some unsigned values using IEEE numeric standard. Signal, red. In all honesty, though, I don't think the. Oh, that's true. The red are the lower bits that I found that out while playing around with colors. The red and the blue are switched. And that does affect the luminosity right here, right? So, and it's going to be unsigned 7 down to 0. Blue. And I think it's really more, this is really blue, green, red from earlier experiments. Those colors are swapped. I've tried to play with them. So let's go ahead and get a process going. Process based upon clock and process. This is a FIFO. We don't really have we don't really need a reset. Oh, I think it's weird because we don't have a in. If rising edge of clock, then and if. And everything will be contained in here, right? Alright, totally. So go ahead and do store red, and that's just going to be signed of RGB 7 down to 0. let's make sure that's correct in our assumption. So here, when we grab the RGB, oh, it's the way this does it. Let's go ahead and grab. Let's go ahead and look at the VHDL and see if it divides it. So let's take in the input, right? And let's just find where these things are divided. What if we look up red? Can I look up red at all? Bad idea. So let's go see. Payload A. So payload A here. So this right here, probably where we're going to go next. So that's 7. It's going to this, which I have no clue. I think that's what we're looking for, right? So that's these constant values. I'm curious. Okay. Numeric. Yeah, this is why we can't understand whatever is happening. Okay, so the issue is I don't know how it's orientating this. If anything, we should assume it starts at low from big. So let's assume that this is correct, and it should be 23 down to 16. And that's just because of the orientation of the other one. We don't know any better. Assume that's how as long as that's how we insert the data, right? Yeah. The system wouldn't know any better. So as long as we insert the data that way. And well, let's see. Go here, stream image processing. We have these JPEGs and we have these bins. So, well, let's take a look. That is clearly blue. Oh. Yeah, HXD, get that out. Go, let's look at that top file. Open, stream, proc. Let's look at, yeah. So we want to look at and there's also the Indianness of this. So let's do two. So highest is right here. So blue is definitely the lowest. And we can assume that when we load it, the Indianness would change. Yeah, so let's go ahead and go that route. So yeah. 15, 8, 7, 0. Okay. Now we want to just do one quick output, so we'll just computation, comp. Let's just go ahead and make these 16, 15. That way we leave room for any additional numbers. Okay, okay. And computation. Now we're just basically going to grab this guy. Do that as one computation. Great. Red, green, blue. So let's try doing that first, right? And then we need a bit shifted by 8. Zero comp. The best way to do that would be to just, and we want to add 16. Weird. But if we're going to do it by 8, might as well just do this. And 0, 15 down to 2. Now for our last step of adding 16, comp 2 equal comp 1 plus 6. And then outside here, we're just going to take our output and do comp standard logic vector of comp 2 7 down to 0. So let's see how this first we should simulate it, right? So make this set as top, make sure it's set as top in simulation as well. We would simulate it and we'll just force we don't really care about the valid right now. See what we get out of this. So yeah, let's restart this. Give it a clock. And apply some values to so here are inputs, so we're gonna force a clock. Period of 10 nanoseconds. We'll start with 0, go to 1. Valid doesn't really matter, but we can force a constant. Oh, force a clock on that. Force a constant 1. RGB value, let's force constant decimal. We want to just do an average. Let's go and see what this value right here, but backwards. So 80s, 8A, like that. Right. Let's run that, what, for 80 nanoseconds. Okay. So let's do make those 7. Well. Okay. So the issues was when you do the multiplication with the values, it automatically added another 8 bits. Well, it actually might add 24 bits. So we might actually have to do we have to make it 24. Yeah. We only care about those ones. I don't know if you can do that. So let us restart. And basically up arrow until we get to all our previous ones. Add a clock. Add valid. Add a hex. Run 80 nanoseconds. So let's see what we got. That's okay. We have our 3 values. And then shifting over it and adding 9A. I wonder what the math looks like for that. Okay, so let's go run synthesis. Curious what we got going for ourselves. Simple grayscale. Let's see what we got at grayscale in HDL online. See what we can find. Grayscale HDL. Color to conversion grayscale. HDL toolbox. First, what's the size? So you can generate code. But I just wanted to see the code. So like there we go. Gray counter. Not what we wanted. We want grayscale. I want to have a grayscale. Okay, we want to go page 473 of this book. Can we go to page 473 of this book? Okay, let's see if this guy has code. Lesson 51. Lessons 51. Oh, it's a paid course. Of course. Because we can't learn this stuff for free. Can we? Just be terrible. Well, let me try it. Just we do a VHDL course. I don't want a gray counter. I want grayscale coloring of grayscale image using FPGA. Oh yeah, we could do that thing. Because I mean, it's a convolutional matrix in itself. This might be a better way. Do it. Um, why did that guy? Interesting. Still not what I was looking for. For 8-bit color image to gray for VHDL. Something like that. Very interesting things. Okay. I mean, we could add the color converter and do a grayscale. Okay, yeah, that should be fairly easy. Right there. They use 66, 129, and 25 versus 76, 150, 29. Okay, let's open synthesize design. I want to see how they implemented the grayscale in this system. Um, so let's see how this is working. Take our input and follow it along, right? So let's take RGB. Go to the schematic. Necessarily that level of the schematic, but we'll take it. Don't need no buffers. Goes into a blue reg. And then we have our comp 0, different stages. Carry 4. So adding. And the carry out. Goes to another carry 4. Which one do you care about? Care about that. Another LUT. And register. Okay. magically all going to the same. So let's see, we do a timing summary on here. We didn't really give it a constraint, so it may not be happy. Worst negative slang is infinity. Check timing, no clock. So let's add a clocking constraint and see what happens. So if we go over here, right, edit timing constraints. Let's create a clock. Create a clock, yep. We can go find a source object. Yeah, sure, find. It's not gonna be that hard. Here, push that over. Select that. We got that clock. We're gonna just call it main clock. It's gonna have a period of 10. Yeah. Rerun. Force negative slash is 2.4 nanoseconds. Let's find out where this is. Right here. So let's see. We would want to let's say we wanted to run this thing on a so we want to run this on a 1 divided by a 142 megahertz clock. So we're looking at a so 7.4. So let's change this period to 7.04 nanoseconds, right? All is that apply. Rerun this. Okay. So it's the blue to the comp register. So we're not meeting timing right now if we were to do at 60 frames per second. So let's go back to the code real quick and let's add a few more stages. So let's divide the multiplications into separate things. So we want those to be the 15s. So we're gonna do red comp R red GB. So comp R is going to equal this. GB. Green, blue. Okay, then we want to just add these up in the final stage right here. So let's see how that affects timing. Okay, so let's rerun synthesis and look at how timing changes. Sure. I'll call it gray. Okay. So we've now looked at the timing and we're going to try to change where the biggest issue, and the biggest issue is between the colored registers and the computation. So we're going to let synthesis run and then we'll go look at that timing again afterwards. Synthesis failed. Let's go figure out what synthesis failed. Source. Oh. What was that supposed to be? It was supposed to be times the number. I think it was 25, right? 25 times that. 25 times that. Oh, it was 129 times green, 25 times blue. Yeah, that's correct. And let's rerun synthesis. I wonder if we could add the 128 at the end, you know? I mean, like, I don't really understand doing the 128 and then shifting it. I should go find that app note. Let's see. Let's go find. It's gonna be Vivado app note Sobel. Go find that code. Is this it? I think this is it. Where's my source? Where do I download the source? I can look at what you guys did. You have a download link. Download the TRD package. The reference designs for this can be downloaded here. Okay, let's go here. Let me log on over here. In truth, you don't have to worry about. They're just wanting to know who got the information. They don't require like crazy approval. Okay, so here we are. We want to look at that guy, I think. Not. We can look at Visual Studio Code. Why not? So yeah, they're adding a 16 at the end. They don't explain why. So exactly the same function we have, and with the 128. Okay, let's go here, right. So shifted by 8. Programmer, what's 100? I want to see what's up. Let's go to decimal 128. Just a 1. We could just added by 17 at the end. I don't know why. I feel like I would totally change it to add by 17 at the end. Because let's shift this by 8. Boom. Oh, I bet that may still cause something to roll over, like a rollover checker or something like that. If it's just adds up to a bunch of F's. I wonder if they want to do that before they shift. Oh, and we have to do. Oh, that's one thing I forgot. We have to do arithmetic shift on the. Actually, no, I don't really care about arithmetic shift, but it's. I don't know. Good questions. Good questions. Arithmetic shift or not. But we should look into that. We'll look into that maybe later. Let's look at open the synthesized design. And report timing. Why not we? Yay, timing. We're doing great. So wait, that computation between vreg and that. So that's where we have the two adders. So we're adding and adding. Now if we split that up in two separate areas, we probably could get better delay. But so far, we're now meeting timing with plenty of clearance. Like one add, the second add, and the other add. So I mean, if we wanted to, we could look at different bits go that direction. Okay. Fun stuff. Okay, so I think the grayscale we should be good with some static values and just multiplying it together. Do we want to do an arithmetic shift? Well, it shouldn't matter because those bottom bits are removed later. I'm curious though. We close out of that. Yeah. They're oh, they did completely different, right? Because I mean, if they do it off their Sobel operator and they have a window, Sobel operator, this is calling Sobel operator, and it's shifting things in through a Sobel filter. Um, okay. Um, yeah, so I think we're good. We've done this. The only thing I would suggest is that we might want to look at is in the operator when we do the shifting at the very end. We may want to make this a arithmetic shift where we bring the ones down. Let me see. Do we have an easy way to do a VHDL arithmetic shift? Shift right, shift left. Oh, so I guess if it's just signed or unsigned, and you do. So, oh, if we had it unsigned. But I don't think it's important in this situation because we don't have any negative RGB values. We just consider that out of bounds, that your co-evolution should produce a positive value. Otherwise, you're going to get garbage. Yeah, maybe. Or, oh, we didn't want to use the limiter. Yeah, so let's try that. So, where signed value. So, what if we made these signed values? Maybe I'd make those signed values. Um, shift to the right by 8. 8. I think we can just leave that. That. Um, Pretty sure we want to do. And yeah, let's just make everything signed. So we're gonna do a shift to the right by 4. Yep. Here we're gonna do a shift to the right by 2. We don't want to do no. And shift 1. Oh, that's no, that unsigned value. What if with that so, but we want to put a 0 in front of it, right? We want like no. Fine with that. So maybe, yeah. Okay, well, I'll check that later, but I think that's good for now. So using the sign extension thing. Well, let's just make it set it as top and see if it will at least wait. Let's go set it as top here. And let's run a simulation. Let's close this simulation. Try running a simulation. And I'm gonna go see here. Left, right, signed, unsigned. Yep, that looks right. Okay, it looks like code worked out fine. But we should probably check the bounds of that with a simulation later. Maybe with a 3x3. Okay, well, thank you for watching. We'll test that. I'll test that later. And on Monday, we'll probably take a break from this and we'll introduce the orange crab. I look forward to seeing everyone, having some company on Monday during the live stream. See you then. Bye.